Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and today we're going to talk about free response question number 2 from the 2022 exam. You know, it's always a good day to study for the AP Chemistry exam. I'm really glad you're here. Today we're going to talk about the second free response question from the 2022 exam. And this is a long free response question, and that means it was scored out of 10 points. Before we get started, I want you to grab your calculator, your periodic table, and your formula sheet. What I want you to do is listen to me introduce the problem, pause the webcast, try to answer it yourself, and then listen to my solution. That's what's really going to help you the most. And then you can keep track of your score as you go. Did you earn the point? Did you not earn the point? And then think about ways you can improve your answer to ensure that you are demonstrating all the chemistry knowledge that you have in a way that's going to help you score better on the AP Chemistry exam. Let's jump right into the question. Methanol vapor decomposes to form carbon monoxide gas and hydrogen gas at high temperatures in the presence of a platinum catalyst, as represented by the balanced equation that we have here. Part A asks, are the hydrogen atoms oxidized or are they reduced in the forward reaction? Justify your answer in terms of oxidation numbers. So what we need to do is assign the oxidation numbers to the hydrogens before and after the reaction. What we find is that the hydrogen atoms are reduced. In methanol, the hydrogen oxidation number is +1. Hydrogen almost always has an oxidation number of +1 in a compound. On the product side, the hydrogen is elemental hydrogen, and like all elements, the oxidation number there is 0. So we're going from +1 to 0, and that's how we can justify our statement that the hydrogen atoms are reduced. The oxidation number of hydrogen decreases, and that's reduction. Pro tip, when you're answering questions like this, lead with your answer and then state your justification. They're reduced, and we know it from the oxidation numbers. And that's really a good strategy when you're writing answers to these kinds of questions. And this was worth 1 point. So you had to have correct oxidation numbers and a correct interpretation. Of course, these long free response questions are long. They can have 7, 8, even 9 parts to them. In the following box, draw the complete Lewis diagram for the carbon monoxide molecule, where every atom obeys the octet rule. Show all your bonding and non-bonding valence electrons, which of course you always should do when you draw a Lewis structure anyway. Get out your periodic table. We see that carbon has 4 valence electrons, and oxygen atom contributes 6 valence electrons. We have a total of 10 valence electrons for this molecule. And we know that carbon, oxygen, nitrogen, and fluorine always obey the octet rule. We're told, though, here in this problem that we want both atoms to obey the octet rule. So now we need to put in our 10 valence electrons. We can start with a triple bond between the carbon and the oxygen atoms, and then a lone pair on the carbon and a lone pair on the oxygen. That gives me all 10 valence electrons. It gives me an octet for the carbon, an octet for the oxygen, and we're set. This is what you needed to do for 1 point. The values of the standard molar entropies of the compounds involved in the reaction are given in the following table. We have a nice little table here with the reactant and the 2 products. Part 1 of C says, use the data in the table to calculate the value of the standard entropy change in joules per Kelvin per mole for the reaction, which we are given. So the strategy we want to use here is that we're looking at the sum of the products minus the sum of the reactants, and we're going to use the entropy values that we were given in the table. It's really a substitute and evaluate situation, but we do need to pay attention to one thing. We do need to note that there's a coefficient of 2 for the hydrogens, and so we need to make sure that we multiply the standard entropy of hydrogen by 2 when we set up our calculation. But once we've got the correct setup, sum of the products minus the sum of the reactants, we can do the math. It comes out to be 220 joules per mole per Kelvin, which is consistent with what we see with the reaction. We do expect an increase in entropy because we're going from 1 gaseous reactant to 3 moles of gaseous product. So that's reasonable. I want to remind you, always make sure you show a complete setup for your calculation. It's not a difficult calculation, but you need to show where your answer came from. So show that setup and the answer. Don't just have answers appearing out of thin air. That is not going to work in your favor. This part was worth 2 points. 1 point for a correct setup, including the stoichiometry, taking into account that coefficient for the hydrogen. And the second point was having a correct answer. Part C has a second part. Calculate the value of delta G in kilojoules per mole for the reaction at 375 Kelvin. And then we're told, assume that delta H and delta S are independent of temperature. That's helpful because that means we can use the delta H and delta S values that we already have. That delta G is delta H minus T delta S. So it really becomes a substitute and evaluate situation. We're told delta H is 90.0 kilojoules per mole. We're given the temperature already in Kelvin. And we have delta S from part C1. And so we're going to use our answer from that. And so we can substitute all of this in. All right, but we do need to pay attention to units as we're working. Notice that delta H is in kilojoules per mole. Delta S is often given in joules. So we need to make sure when we substitute into this equation that delta H and delta S are both in the same units. I tend to do these problems by taking my delta H and putting it into joules. You could take your delta S and put it into kilojoules. It all comes out the same in the end. Just make sure you're doing it correctly. I've got my setup here. I can do my math. I get an answer of 7,500 joules per mole. I was asked for an answer in kilojoules per mole, so I need to divide by 1,000. So I'm going to report my answer as 7.5 kilojoules per mole. And this was worth 1 point for doing all of this correctly. Of course, there's more to the problem. We know that. The following particle level diagram shows a representative sample of the equilibrium mixture represented by the equation that we've been working with. Part D says, use the information from the particle diagram to calculate the partial pressure of carbon monoxide at equilibrium when the total pressure of the equilibrium mixture is 12.0 atmospheres. So as soon as I see this problem, I immediately think mole fractions. Moles of what I want over total moles can be a really useful strategy. What I notice is that there are 3 carbon monoxide molecules out of a total of 10 molecules. I can use that really as my mole fraction is really 3 out of 10. The pressure exerted by gas X is the moles of X over the total moles, or my mole fraction, times the total pressure. So I can do 3 over 10 times 12 will give me the partial pressure exerted by just the carbon monoxide molecules, and I get an answer of 3.6 atmospheres. This is what I needed to do to earn the 1 point for this part. Make sure, of course, you've got that work shown and not just an answer appearing out of nowhere. Part E asks us to write the expression for the equilibrium constant Kp for the reaction. Well, we do have the balanced equation, and we know how to write Kp expressions. The basic rules, we write products over the reactants, the coefficients become exponents. But the other thing we have to remember is that we were specifically asked for a Kp expression. And so we need to write this expression in terms of the partial pressures and not in terms of concentrations. So no square brackets here. It needs to be the pressure of the carbon monoxide times the pressure of the hydrogen squared over the pressure of the methanol. And that's what you needed to write to earn the 1 point. The reaction system represented by that equation is allowed to achieve equilibrium at a different temperature. The following table gives the partial pressure of each species in the equilibrium mixture. And there they are in the table. What does Part F ask us to do? Use the information in the table to calculate the value of the equilibrium constant at this temperature. It doesn't even matter what the temperature is. It doesn't go into the calculation. We already had a Kp expression from Part E, and now we just need to substitute and evaluate. So we have the partial pressure of the carbon monoxide times the partial pressure of the hydrogen gas squared divided by the partial pressure of the methanol. And we get an answer of 110, reported with 2 sig figs here. Remember, always show that complete setup. Don't have answers just appearing out of nowhere. And this is what you needed to do to earn the 1 point for Part F. Part G says, the volume of the container is rapidly doubled with no change in temperature. As equilibrium is reestablished, does the number of moles of methanol increase, decrease, or remain the same? Justify your answer by comparing the value of the reaction quotient Q with the value of the equilibrium constant Kp. There are a couple of ways, actually, that we can answer this question. Critical feature here is that you have to recognize that after the volume doubles, all the pressures are initially halved, and then we have to reestablish equilibrium. Knowing that, we can easily calculate the new pressures after the volume is doubled, but before we've reestablished equilibrium. So the methanol pressure would go to 1.35. The carbon monoxide partial pressure is 2.2 atmospheres. The hydrogen partial pressure would be 4.2 atmospheres. And so what we can do is substitute these values into our expression for Q, and then compare it to K. So we can calculate Q by substituting that in, and we get a value of 29. Now we had a value from K back from a couple parts ago, and we see that Q here, 29, is less than the value of K that we had calculated, which was 110. Because Q is less than K, that's telling me I don't have enough products. I need more products to reestablish equilibrium. I need to use up some of my reactants, so the system will proceed in the forward direction to reestablish equilibrium, and therefore the moles of methanol will decrease. That was one way to solve the problem. Like I said, there's another strategy. It's going to get us to the same place. It's just another way of setting it up. Keep in mind, yes, that after the volume doubles, all the pressures halve initially until we reestablish equilibrium. And so instead of calculating the new pressures, we could just say, okay, they all get divided by 2. 1/2 of the original carbon monoxide partial pressure and half of the original hydrogen partial pressure, which of course then gets squared. And then we have half of the initial methanol partial pressure. And so we can say that Q at the end is 1/4 of K, which of course is smaller than K. All right. And so if Q is less than K, we're still going to proceed in the forward direction, and the moles of the reactant, methanol, will decrease as we reestablish that equilibrium. Either way, we have enough work to support our answer. This part of the question was scored out of 2 points. 1 point was for correctly calculating Q, either numerically or just how it compared to K. And the second point was for correctly comparing Q to K and interpreting it appropriately. How did you do on this problem? The average score on this question in 2022 was 5.29 out of 10. So it was a fairly high scoring question, probably the highest scoring free response question on the AP exam in several years. Certainly the highest scoring free response question in 2022. Doing well on this question means you scored at least 5 points. If you were doing 6 points or higher, then you're really in good shape here. If you found this helpful, like the video and leave the comment, and don't forget to subscribe to my channel so that you get all my latest updates, all my review webcasts, and you really are ready for the AP Chemistry exam. Remember, it's always a good day to study AP Chemistry.